So, like you heard, we're here to give you the ROS2 update. I'm Deanna Hood.
And I'm William Woodall. We're both at OSRF. We have a QR code here and a Google short link. There's some diagrams in the presentation, so if you want to follow along, potentially it might be useful.
So we'll get started. As we are aware, not everyone in this room might have heard of the ROS2 project before, so we'll start off with an overview, go into some high-level overview of the features that have changed in the last year and some implementation details of a few of them, and our experience in the last year working with real robots on ROS2, the Turtlebot specifically, and the roadmap of what's headed in the future for the project. So when talking about the motivation for ROS2, it usually helps to start looking at ROS in general. And we see ROS as made up as a bunch of different components, namely the plumbing at the core of everything that allows you to pass different pieces of information between the parts of the system, as well as tools for visualization, capabilities for navigation, for example, and the ecosystem of thousands of packages that are available to you as a community that is what allows things like ROSCon to be possible. ROS has been used on thousands of different robots now, and each of those robotic systems has a set of different characteristics. And depending on those characteristics, different systems will make use of different parts of ROS. So, for example, the PR2, systems using the PR2 are typically characterized by having a research focus. They've got lots of sensor data to process, but also lots of computational power. The PR2 on board has 2 high-speed computers connected with a near ideal network connection. And as it was the first robot using ROS, you see most of the tools that were developed early on and at the early stage of ROS have this sort of system in mind where, with this set of characteristics. But of course, over time, in the last near decade, there have been a lot of new use cases that have come up. For example, drone delivery startup is going to have a lot of different characteristics for the robotic system. You're going to be more concerned with power consumption as you move towards production. You've got smaller processors on board, drones coming in and out of contact with each other. And as this is quite a large contrast from the system with the PR2, and even this system wasn't necessarily even around in 2007, if you think about it. And so what you find is that some of the tools and the ROS infrastructure start to break down a bit with these newer use cases. For example, ROS doesn't deal too well with the unreliable network connections between drones, and the relatively large amount of computational resources on the small processors can be an issue. So we know that there are areas where we can improve ROS to target some of these newer use cases. And we have identified a few of those as the goals for ROS2. So multi-robot systems I spoke about, but also allowing you to use the same code for prototypes as you use in production, pushing ROS2 as far down onto the devices as possible so that it works better in these situations where you have lots of small computational units cooperating, as well as better support for real-time systems and Windows, as we know that these are important to a lot of our users. So, comparing with the diagram before then, how ROS2 would compare with ROS1. Where in ROS1, the plumbing was all pretty much custom from top to bottom. In ROS2, what we've done instead is to reuse what we can from DDS. And this is an industry standard that's then implemented by different vendors. And it's been used in a lot of high-risk, high-visibility scenarios like medical industry, financial services, space exploration. And with that comes with a lot of credibility in terms of sort of production quality. But in addition to that, it has a lot of features that are just inherently applicable to these modern robotic systems. So for example, you've got masterless discovery, and we know, for example, that The centralized discovery protocol in ROS1 is a blocker for a lot of multi-robot systems, whereas this is something that is just inherent in DDS. In order to use DDS with ROS, we've had to restructure kind of how ROS is set up. And so where in ROS1, your user code is going to tap into the ROS API, and that will speak directly to the network. In ROS2, the ROS API acts as more of an abstraction layer, and then the actual work of sending data to the network goes through a DDS implementation. And this can be one of a few different supported implementations. We'll go into more details about that in a minute, but in general, they all have the common functionality of masterless discovery, for example, and other features that allow you to have higher level of control over the specifications of the transport. So if you were at ROSCon last year, you might have seen one of the demos that we gave, which was a quality of service demo, that since we have, this is a feature that is inherent in DDS, and then we've exposed to the ROS API that allows you to have finer control over the network settings, so that not every packet has to be acknowledged and this sort of thing. And you have quite a wide variety of settings that you can tweak, and this is an example of something that comes out from using DDS underneath. So if you haven't seen these demos, I would encourage you to check them out. They give a good overview of how the state of ROS2 as it was at ROSCon last year. For now, we'll focus on what's new this year. So there have been a lot of changes. Of course, there are going to be more than we'll be able to speak about in this talk, but to summarize some of the key user-facing features I've presented on this slide, I also noted the alpha that they were released with, so that if you're interested in the implementation details, you know which time, like period of time, to go check out the different code changes. But in general, support for more DDS vendors, programming languages, and platforms. So we'll go into more detail about the Turtlebot later, but we've improved our ARM support, for example. Actually, it was a community member that tried out ROS2 on the Raspberry Pis for the first time. We work with the Dragon board, this sort of thing. But moving these aside for a minute, because in addition to the user-facing features, you also have a lot of changes that have happened kind of beneath the surface. And these are often tightly coupled to the user-facing feature, but just to give an example of something that might seem like a straightforward feature is the functionality for a node to wait for a service to become available before it calls it as a client. This underneath requires a whole infrastructure of providing notifications of when there are changes that happen in the ROS graph, like nodes coming online, or in this case, a particular service coming available, and making those notifications available to the nodes. Similarly, the Python client library, to make those changes, required a lot of reshuffling underneath the surface that we'll go into more details about later. For now, we're going to focus on adding FastRTPS as one of our supported middlewares and work that was involved in that. So, like I mentioned, you can use a variety of supported DDS implementations with ROS2. The reasons you might want to switch between them, it's going to depend on the particular project that you're working on. So, for example, you might find that a particular implementation has a license that works better for your case, or works better on smaller processors, is certified for space travel, this sort of thing, as well as diagnostic tools that the vendors will provide. And what we allow you to do is that actually you can write your code and then switch between different supported vendors without having to recompile. And part of how that's achieved is through this ROS Middleware API that kind of acts as an abstraction for all of the different vendors that are underneath. Because this diagram is obviously a simplification, and DDS, as I mentioned, is a specification that's then implemented by different vendors. And so what you find is that there are variations on exactly how those implementations are done. And part of what's done in the ROS Middleware API is to absorb the differences in those implementations, kind of smooth out the variations between the vendors so that from code that's above that layer, all of the vendors present they're seen equally in the eyes of ROS. And if you consider then what we're speaking about when we say that we added FastRTPS as one of the supported ROS middleware implementations, what we're referring to is the work that goes into adding this sort of block in this adapter that allows then FastRTPS to be used underneath and plugged into the system as one of the ROS middlewares. So we have, until recently, been supporting 4 different DDS implementations. Of course, there's a lot of work that comes with maintaining multiple. And so what we have done recently is cut that back to 2. FastRTPS being the default, and then connects from RTI in addition to that, because the 2 combined allow us to exercise all of the features of the API that we're looking to test our sound from a design perspective. If you might be wondering what it is about FastRTPS that we're interested in that would prompt us to add it and then make it our default. So FastRTPS is open source. They've recently changed their license to Apache 2.0, so free and permissive. And even though it's not necessarily a fully fledged DDS implementation like the other vendors that we support, it's more of a lightweight implementation of the core wire protocol. And so where there were features that were missing in the implementation that we were making use of in ROS2, Eprosima, the organization behind FastRTPS, has been very helpful in working with us to add those features so that from a perspective of the user, now they all present the functionality that we need in a ROS middleware implementation. Conveniently, they also FastRTPS can be integrated seamlessly into our toolchain so that we can package now from top to bottom a ROS2 system, vendor included, that is Apache 2.0 licensed. So hopefully this gives you an idea of some of the background work that is behind. Maybe you just see a 1-sentence change log that's added support for FastRTPS as a middleware implementation. And this is to give you an idea of the work that is behind that. Moving on to the Python client library, which is something that we know that people were looking forward to in ROS2. Like in ROS1, you can have nodes in ROS2 that are written in different programming languages, and they're able to speak to each other. And how each node is implemented is through a ROS client library that is in the respective language. And so these client libraries are designed to be implemented in a way that is supposed to feel kind of natural to the respective language, so Pythonic in the case of Python, and it shouldn't necessarily feel like you're being forced into a C API. And where these sit in the ROS stack is between the user code at the top and the middleware interface at the bottom, which we mentioned is kind of what encapsulates the core functionality that's necessary in order to then build the rest of ROS on top. The sorts of functionality that you'll find in a client library are the things that sort of ROS is known for, the things that you think of when you think of ROS mostly, so that names can be put into different namespaces, that they can have parameters associated with them. The functionality that we think adds a lot of, brings a lot of benefit to ROS users. But in addition to those features, you'll find some things in the client library that maybe you wouldn't necessarily consider features as themselves. So for example, the threading model, like what happens when you call spin, and that then has to go and start up different threads to actually run the code, or if you want to bypass network communication, if you're running nodes within the same program, then inter-process communication is something that you'll be able to take advantage of, but it's not necessarily seen as like a user-facing feature, it's more under the hood. And these last two in particular are parts of the client libraries that tend to be actually specific to the programming language that they're implemented in. So for interprocess communication, for example, you're going to need to know about higher level concepts, things like memory management and types. And the threading model, for example, is going to be dependent on different libraries depending on what language you're using. And what the rest of those features are, though, it's mostly more like behavior or logic, and these things ideally should behave the same regardless of what language the client library is implemented in. So there's a lot of opportunity there for the client libraries to share that core functionality. So this is what we have done. We've broken out the core functionality of the client library into the ROS client library, and then the programming language specific client libraries build on top of that to fill in what's missing. And by doing this, we hope that the client libraries of the different languages are smaller and easier to maintain. But more importantly, we find that they're more consistent. And in ROS1, in comparison, you have the Python client library was Python top to bottom, and it was a completely different implementation to the C++ one, which meant that if you ever found a bug in parameters, you would have to go and fix it in multiple places. Whereas in this setup, if you decide to change the behavior of console logging, then you update that in one place, and all of the client libraries will then be updated at the same time. And this isn't just client libraries that we implement, but any client libraries that are contributed by anyone that wants to tap into RCL. So the C# and Java implementations have actually been contributed by community members. And we have implemented the ROS client library, the RCL core in C, because that's one of the languages that's then typically the easiest for other programming languages to wrap with foreign function interfaces. So to give you, drill down more into the details about what this communication between client libraries using different languages looks like, I'll pass over to William to run through an example.
Oh, thanks, Deanna. Yeah, so I'm going to drill a little bit more into detail about how this stack works, basically following a message as it goes from publish and it's received by a listener, published in a talker and received by a listener. So if you consider the really, common example of a talker and a listener talking over chatter, if you've ever done the ROS tutorials, this probably looks somewhat familiar to you. So if we take a look at the talker, it's very familiar, probably, very similar to what you would see in ROS1. We create a node and a publisher, and then in a loop, we're going to populate the data in a message and publish it, and it'll say hello world and increment each time it publishes. And so where we're going to drill down is where you actually do the publish call. And so at this point, it goes into the implementation of RCL-Pi, which is actually written in C. A lot of it is. And this is what's called in Python a Python extension, and a lot of programming languages have this concept of extending the language using C. Sometimes other languages like C++, but most commonly C. And so there's a lot of stuff here. The big things to see is that we're basically passing in the publisher object and the message the user wants to publish. And then there's a step here where we convert it from the Python message that the user was using and manipulating, and we convert that to a message that the underlying middleware can digest. And then finally we call RCL publish, where we're now passing into the language in specific part of the system. So up until this point, we're in sort of Python land, and would be different depending on which language you're using. But now we're passing into this common core piece of the system that Deanna described before. So looking at this function, it's actually relatively simple. It's essentially passing along the publisher object and the message the user wanted to publish, and passing that along to the next interface. And so I want to stop here for a second. You might be asking yourself, well, it seems like we have a lot of redundant interfaces we're passing through. And for publisher, it's a pretty straightforward thing. It's a concept that exists at every layer of the system. If you took a more complicated concept, like parameters, for example, parameters might be represented in RCL-Pi and RCL, but wouldn't necessarily be represented in an ArmW. It would be built on top of the other primitive middleware concepts like publish, subscribe, or services. And so the other reason to have this code here is that if we want to do something like collect statistics while publishing, like how much bandwidth we're using and how often the messages are being published and things like that, this is an ideal place to do it, because if it were higher up in the language, you'd have to do that for every single programming language you want to implement. If you pushed it down, then it would have to be implemented for every single DDS vendor you wanted to back the system. And so that's why the RCL is sort of the sweet spot for, you want to push as much code there as possible and behavior to prevent from having to reproduce it in multiple places, and increases the chance that that there's a bug in multiple places, or you have to update multiple places when you want to change something. And so this ArmW that we've been talking about, it's essentially just a set of headers which define some functions and some types. It's actually not the actual implementation. And so here it's really simple. It's just takes a publisher and a message and returns a return code. And it's in C. And then under that, there's a there's an ArmW implementation is what we refer to it as. And that is that adapter that Deanna was talking about, which adapts the DDS vendor at the very bottom, which actually does the work, to this interface we've defined that's got this primitive, minimal set of things in it. And so in a particular case, if you're using FastRTPS, you would be using FastRTPS in those DDS vendor boxes, and you'd be using our adapter for that, which eProsima helped us a great deal with and actually started, which is the ArmW FastRTPS CPP. And that's the code that maps from our concepts to the underlying systems concepts. And so taking a look at particularly the case of FastRTPS, you have the implementation of this function that was defined in the interface. And you can see here we're doing some stuff like creating a serializer, and then we're using that serializer and the message the user gave us, which is a ROS message, to serialize it to the wire format, to marshal it. And then finally we call the FastRTPS publish call. This is a bit, a lot of the details are hidden here because there's a lot of little moving pieces, but essentially we're serializing it and then actually calling publish to send it to the wire. And then of course our hello world message has now been sent over to the middle here. And at this point I want to talk a little bit about the listener. So it's always sort of hard to describe these situations because you've got two concurrent systems running, but the whole time the talker was running, we were also running the listener. And again, this is an example in C++, but again, it should be relatively familiar if you've done the ROS CPP, ROS1 tutorials. We're doing things like creating a node, creating a subscription on the chatter topic, where we pass it a callback to get called when new data comes in, and we're calling spin eventually. And most of this work is that is broken a little bit, sorry. There's supposed to be an arrow, a box surrounding spin that points to this box. Most of the work is happening in this spin function. So everything that happens up to that is just setting up, and then your program's going to spend most of its time in this spin function. And so if we look at what that spin function does, it basically sits and does a non-blocking, it does a non-busy wait. So it waits for data in an efficient way, waits for something to happen in the system. And so once we got our message from the publisher into the middleware, there's an event that wakes up that waiting. And so now our spin function knows that data has been delivered, and so it needs to get that data out of the middleware and give it to the user's callback. And so basically it checks to make sure that the subscription has data. If it does, then it calls this execute subscription function. This execute subscription function is a bit, it looks a bit complicated with all the namespaces and template arguments and stuff, but essentially what's happening here is that the system has already determined that this subscription has data available on it, and so it's creating a message to store the result in, and it's calling the next layer, the RCL layer, and it's calling take. And this is the function you call when you know that the system has data available for you. You can take it out of their buffers. And so basically we're passing this message to store the data in and the subscription to the RCL level. very similar to the publisher side of things. And again, sorry, let me back up. Again, we've just passed across the language-specific barrier. So now we've left C++ and we're going into this common core. So if we were to look at a listener written in Python, we would now be at the same place. And so again, just like in the RCL publish function on the other side, this is a relatively simple function where we're passing directly down to ArmW take. But again, it would also be an opportunity in this place to do things like collect statistics, or if you wanted to do something like topic aliasing, where you're telling it, I'm publishing on this topic, but also publish it to this other topic. You might handle that kind of logic here. And so here, basically, we're passing the subscription down and the message down. And again, the ArmW interface is just a header. It's just a definition. The actual work is happening in this adapter code for FastRTPS. And here you can see that we're creating a buffer to store the data in temporarily. And this is like the binary. This is still serialized. And so we take it from FastRTPS. This is this line here is the line where we actually take the data from FastRTPS. And then we check to make sure it was actually contains data. And then if it does, we deserialize it and set taken to true. And at this point, this is where we come back up the stack. So essentially, we've taken the data and deserialized it, and then it returns back up this what we just drilled down, and eventually gets delivered to the user's callback. But you can see that the point to drive home here is that we're sharing a lot of code between the two languages, and we're also trying to, like Deanna said, smooth out the differences between underlying vendors by having a really simple but well-defined interface in the ROMW interface. And the last thing we're going to talk about is we did do some work since the last year, just sort of for fun and to see where we were at, and to to play with real robots once in a while, because we don't get to do that as often as we like. And we wanted to port some minimal viable demo of the Turtlebot 2 running on ROS 2. And so what we defined as that is a Kabuki driver, which is if you're not familiar with the Turtlebot 2, it's the black disk robot that's at the very bottom of the stack. It's made by Eugen. And we also needed a driver for a depth sensor. In this case, we were trying out the Orbeck Astra driver, or Orbeck Astra camera. And we needed a joystick driver to test out driving it around, and we wanted to implement the follower node. And again, for those who are not familiar with the Turtlebot demos, the follower node is just a program that reads data from the sensor and then uses that data to try to follow you around with the Turtlebot. So the way we ended up doing this, so this slide is basically how we ended up, and then I'm going to go into a little detail about other things that we tried. For the Kabuki driver, it's actually a really modular set of software. There's quite a lot of packages that are under the Kabuki driver in ROS 1. But it turns out that it was designed quite well, and the vast majority of the code is not specific to ROS CPP, the actual network part of ROS 1. And so all we had to do is install the Debian packages for the dependencies of that, like all the code that actually talks to the Kabuki and does all the hardware communication and stuff like that. And then we wrote a very thin ROS 2 wrapper on top of that. For the Astra, we ended up taking the ROS 1 driver. It wasn't separated in the same way, and I don't think it necessarily made sense for it to be separated in the same way, but for better or worse, it wasn't. And so we ended up forking that and porting it by hand to ROS 2. For the joystick driver, that was really simple, so we just wrote that one from scratch. And for the follower node, we also forked and ported that one. And then anytime we needed to do debugging or visualization, we'd use the ROS 1, ROS 2 bridge, which I won't go into too much detail here. We talked about it in previous ROSCon talks, so if you're interested in that, there's a demo on our tutorials and demos on our wiki, and there's also a bunch of stuff about it in previous talks. But I also wanted to talk, so you can see here mostly what we did was just replace the ROS 1 code with ROS 2 code. But we did try some other things. And I think what it came down to is that most of these examples were either really simple or trivial to convert, so it wasn't worth using some abstraction to do the conversion, or they were very complicated and we didn't have time to make an abstraction that was good enough. So One of the things we tried was a shim, and we talked about this in the past. And what I mean by a shim is the idea that you have some code that uses the ROSCon API, maybe in C++, for example, and the shim's purpose would be to present that same API to your code, but be implemented by ROS2 under the hood. So ideally, all you'd have to do is, with some different build configurations, recompile your code, and it would just work with minimal to no changes. We tried this, and a lot of things worked. All the stuff we did on it is on my colleague Morgan's GitHub account, which I've linked here. It worked for the simple cases, but it also, particularly with the case of the Astra driver, it used a lot of really advanced functionality in ROS1, like custom serialization of message types. It made use of other parts of the system that were part of ROS1, but not what you would consider part of ROS CPP, things like image transport and message filters and TF and stuff like that. And so one of the problems we had was finding the right, I use the word strata, which I tried to explain a little bit with this diagram, find the right strata in which to put the shim. So you can imagine you could only shim the ROS CPP API, but then you have a choice of, do you bring all of message filters and all of TF from ROS1 and put that on top? Or another option would be, we have TF ported to ROS2. Would you instead provide a shim for the TF API and use the ROS2 version of TF under it? And so you have a little bit of a choice as where to draw this line, and it wasn't clear to us where that line should go just yet. But we have been working on it, and it'd be interesting to see what other people thought about that. And so ultimately, the Astra driver needed so many features that it was, we couldn't make a shim that was complete enough to really just recompile with no changes. It did work for some pretty simple things, like the joystick driver probably would have worked and stuff like that. The other thing that I know there's been a lot of consternation about is we've made some changes to the build system in ROS2, which are different from ROS1. And so we're trying to find ways to minimize that change or to eliminate it altogether if possible, or at least give choice between the two if you're uninterested in the changes in the new one. So I think this particularly came up when Brian was trying to convert the Kabuki stack, because it had lots of catkin packages. In the end, he ended up just using the catkin packages as a dependency and building a very small thing on top of that was ROS2. But in the meantime, he wrote quite a bunch of documentation about his thoughts about this on our wiki, so if you're interested in that, I recommend you have a look at it. But just to summarize some of that, we wanted to try find ways to make the two systems more similar, ways that we might be able to change catkin to be more, to have some of the features of Mint, or change a Mint to be more like catkin, where the changes we have exist currently are maybe unnecessary or only aesthetic. We also wanted to make sure we could mix catkin and Mint, and that's what I was talking about before. And that's what we ended up doing actually for the Kabuki base, because all the packages that actually talk to the hardware of the Kabuki are in catkin, and the thing that Brian wrote as the small ROS2 wrapper on top of that is using a Mint. And so unlike, if people are familiar with the transition from ROS build to catkin, there was this rule where ROS build could depend on catkin, but not the other way around, and that caused sort of like a forced migration. In this case, you shouldn't have any constraint like that. It would be catkin can use a Mint, Mint can use catkin, because at the base of it, they're both just CMake. And so it should be easier to mix and match them in the transition and in the near term. We also, he talked about our thoughts about this idea of a non-homogeneous workspace. So already in ROS1, you can have a build which has both catkin packages and plain CMake packages, if you like. And this would just be an extension to that, where you have catkin packages, plain CMake packages, and then maybe a Mint packages, or maybe pure Python packages, which is something else we have in ROS2 that we don't have right now in ROS1. And then, of course, ideally, we just have one build tool that works on both of them, so you don't have to learn different tools for different systems. There are some conceptual details we need to figure out, but I think we're trying to think about them early and often and figure out ways to deal with them. For example, some people will be familiar with the fact that catkin will always produce a setup file in your wherever you install your code to. That's really convenient as a developer, because you just source that and it sets your environment up with the right path and library path and all that stuff. But for things like packaging and stuff like that, it's sort of a non-standard pattern. In a Mint, it's completely optional. Every package installs its own setup file in its share folder, so it's sort of insulated and isolated from the rest of your packages you've installed to your install destination, which should also make it easier to release it for Debian, for example. If you want to install a user, they have rules against where you can put files and things like that. And so one of the things we're thinking about is trying to figure out how to make it optional for Catkin, but not make it inconvenient for people currently using it and stuff like that. Also the devel space. So the devel space is something that I think provides a good deal of utility for people, at least for some developers that want to have a really quick build, compile, test, change cycle. But unfortunately, it adds a lot of complexity to Catkin. I'd say almost half the code is dealing with the difference in devel space and install space. And so in a Mint, we wanted to try something different. And this is a good reason, in my mind, we had the freedom to change things as we saw fit to see what works and what doesn't. We have what we call a symlink install. So basically it does the normal CMake install step, but rather than copying files, it symlinks them. And so you get sort of the benefit of the devel space without having this extra concept that's unfamiliar to other CMake developers and most developers in general. And so perhaps one option is to backport this symlink install feature to Catkin, but it's an open question about how to deal with that discrepancy in the tools and stuff like that. And of course, avoiding documentation confusion and stuff like that in tutorials and knowing which to use when. And with the ultimate goal of taking the things we found that work really well in a Mint and trying to make Catkin more like a Mint and vice versa, and try to eventually, ideally, we'd eliminate any of the differences. But we'll just have to see how that goes. But we are looking into it. I don't have any definitive conclusions like to tell you, if you're going to try ROS2 and want to port some of your ROS1 code, the truth is there's a lot of different options. It depends on the code you're converting, how complex it is, and what its dependencies are, and what you'd prefer to have as the end result. So we're still sort of exploring all the options and trying to support as many of them as we can. Finally, I want to end with a roadmap. So we've been telling everyone we're going to have a beta 1 for ROS2 at the end of the year, and we're going to try to hold to that. I'm not going to try. We are going to hold to that. Brian, get in trouble with Brian if I say anything else. So what we'd like to have for the beta is an idea of composition, which is, if you're unfamiliar, it's like how it's this idea that you can write a node and you can either have it in its own process or you can combine it with other nodes in a single process, and that detail should be a runtime decision, not a coding time decision. We want to do some more benchmarking. We want to improve the default behavior. There's a lot of quirkiness still with our default behavior in ROS2 about default quality of service settings, default network configurations, and things like that. We want to improve those. We want to sort of clean up and organize our design docs. We have a lot of stuff out there, but some of it needs to be updated and organized. Of course, tutorials and examples, expand on the ones we have, and really focus on people who want to learn how to use ROS2. Command line tools, we've been working on that a little bit. In Alpha 8, we have a very, very simple, but nonetheless exciting ability to ROS topic list and echo in Python. Using Python, we finally got our Python API to the point where we can implement some of these features. And of course, we want to improve the ROS1, ROS2 bridge by adding support for services. There's some other things we'd really love to do, but we're going to see how much time we have. Console logging is one of them. Another one is a higher level orchestration, which is sort of related to composition, but it's more like the functionality of ROS launch. And then in addition to that, the ability to verify the system you've described, because that's like an open question always with ROS launch. Like, I ran ROS launch, is my system ready? And you're like, maybe. You look at a leaf topic and hope for the best. So we'd like to improve on that, and some dynamic behavior, like especially in multi-robot systems, the ability to change things at runtime as robots enter the system, or you add a sensor dynamically, things like that. We also have some pointers here to some documentation, to the ROS wiki. We have some developer docs that we're working on. Hopefully get a better generated, polished looking developer docs, but we've been working on the content at the very least. And also we have the design docs, which we've had for a while now. So have a look at those. And with that, we'll take questions for 50 seconds.
I'll make it quick. So in terms of timeline, you've talked about when a beta is coming out. When do those of us who are sort of deploying production robots, when should we start taking this seriously? That came off a little more hostile than it sounded. When can we start using it?
The answer is,
I
don't know. I mean, for everyone out there that does software, development, which I'm sure is most people out here, planning is very hard. The system is also very large, and our resources fluctuate over time. So, if we get a lot more people working on the project, either at OSRF or abroad, then potentially pretty soon. It's a hard thing to answer. It's sort of, we're working as hard as we can, and when the feature set's there that you need, then maybe you consider doing it.
Thank you.
Yep.
Hi guys, good work. Thank you. I have two notes and a question. One note is if you want to do the benchmarking, we are doing evaluation already. My name is Adam Dabrowski, and my friend and me, we did the evaluation of ROS2, so we should talk in the coffee break, I guess. I would like to go to slide 22 for my question, actually. It's concerned with abstraction of the DDS, because from my experience with ROS2 and with DDS, I think it's not that easy, because DDS provides quality of service, which is the benefit of having it. Actually, if you want to abstract DDS from, so that the ROS is agnostic to DDS, you're going to lose that. So, as I see it, right now ROS2 has like 4 quality of service selected. And in my belief, this is a very small subset of DDS. Yep. So actually, what are your plans concerning development and extending this available QoS settings?
Yeah, so let me just make sure I have the question right. So basically, we've got this abstraction layer on top of DDS, and part of the problem is DDS has lots of features, and we're only exposing a small set of them. And the question is about our plans for that. Is that right?
Yeah, are you going to extend this small set?
Yeah, so the first thing we wanted to do was try to extend it with, we wanted to have enough features exposed to emulate what we had in ROS1, and then maybe just a little bit more. We do want to include more of the quality of service features that are available in DDS. We just want to find a way to do it that doesn't necessarily tie us to one way of describing those, or necessarily ties us to DDS. As you said, this is a very hard thing to do. Eventually, we'll probably end up exposing many or most of them. The other thing we have, which sort of our judgment there has to be about which features do we think will be useful to the majority of users and which ones are sort of really niche features. And one thing we'll have, which was not in any of the diagrams here but is in the developer docs, we have this idea of a package where you can give it a ROS thing, like a publisher, and you can get the underlying DDS thing back, and you can do anything you want to it. Now, you have to deal with any consequences that come with that, but that's a way for us, who people really need a particular feature, can get access to it without exposing it to everyone or requiring it of every underlying DDS vendor. So, yeah, but we should definitely talk. It'd be great to hear what you...
Yeah, we will.
Yeah.
Thanks, Deanna and William. I have one question. Is there Raspberry Pi implementation on ROS2 and FastRTPS? Is there any detail? And the other is, did you natively compile on Raspberry Pi 2, or you use coarse compile? Thank you. So
the question is, are there any details about using ROS2 with FastRTPS on a Raspberry Pi?
Yeah.
Yep.
Yeah.
I don't know if we've done OpenSplice, but have we done FastRTPS yet? Yeah, so as far as we know, it works. We just haven't documented it yet because, as I said, one of the things we did in the last year is, worked with eProsima to get some of the missing features we had. So when we originally did the Raspberry Pi stuff, FastRTPS was missing 1 or 2 features, so we did it with OpenSplice at the time, but I don't see any reason why it wouldn't work. You had another question about compiling, maybe, or I don't.
Because you compile native on the Raspberry Pi to take a long time. Yeah, just.
Yeah, it takes a long time. So we've been trying to get, we have a build farm to build binary packages, and by binary packages I mean like a tar file with everything in it, which is pretty primitive, but it does work pretty well. And we have some experimental ARM jobs for that, so hopefully you won't have to compile it on the Raspberry Pi, you can just download the binary, but I don't think we're quite there yet. Pretty close though.
Okay, thank you. Yeah.